So the velocity of sound, oh, okay, so the velocity of sound is going to be dz dt, right? Because it's going to be the rate at which the sound wave is traveling in this direction, towards the person. So then, 331 1 plus t over 73 1/2 is equal to what? dz dt. But then we have that the temperature in the air is a function of the height, right? So then what's the equation telling us? When the h equals 0, the temperature is 20, right? So m times h plus b. It's like a linearly decreasing function, right? So the original temperature is going to be what? 20 Celsius. And then it decreases by 2 Celsius for every 1 mile. So what is that information giving us?
-2.
Huh? That's the slope, right? For every 1 mile up, the temperature is decreasing by 2. So the slope would be what? Minus 2 over 1, right? For every 1 mile. Is that right? Where h is measured in miles, right? So let's see if that equation works. If h is, this is miles and this is miles, right? So if h is measured in miles, for 1 mile, the temperature is going to be 18. For 2 miles, the temperature is going to be 16. Right? Does that make sense? So by the time you reach 10 miles, what is it going to be? Oh, 0 Celsius, right? Yeah, so that makes sense, yeah. Do we have to convert that to meters?
I think so.
See, if I keep it this way, the h has to be measured in miles. Let's see here. Okay, let's just keep that in mind, because when we're using 331.4, that's meters. So we might have to convert some point just to make sure everything is right. So now let's see here. 1 plus, and then the t, I can then substitute this guy in there. So negative 2h plus 20 over 273.15 square root. Okay, so now I need, the time to go over here, this one can come down here. I need some kind of a relationship that ties z to the variable h, right? So that I can make this, I want to make this eventually dh, so that then I can integrate it, because this is right now dz. This is the distance that is traveling this way, right? So I need some kind of relationship between z and h. How do I create that relationship? Well, this is it, right? So let's see here. So 331.4 dt can go over there, is equal to dz over 1 plus then I can integrate this 0 to t, but then how am I going to integrate that, right? Because these two variables are different. See that? So how would I do that? Let's see, dz, I can say, if I do dz dt,
Why don't you just
oh, you know what, I can make a ratio, I'm thinking.
Z equal to-
Isn't this the same thing as in Calc 1 where you make a ratio similar triangles? You can say this distance to this distance is the same thing as this to this, right? Or you can say this to this. Yeah, I think that's the one, similar triangles. Yeah, it's better than this one. You could do similar triangles. You can say any z to any h is equal to this total z, right, divided by 10. You see what I mean?
Yeah.
Ah, similar triangles, Calc 1. Right, z to h is equal to, so what's that total z? Square root of 10 squared plus 50 squared over 10. Is that right? Therefore, dz is equal to that times dh. Yes, yes, yes. So h goes over here. dz is square root of 10 squared plus 50 squared over 10 dh. Then put that here. You got it. Okay, so the integral of this is 331.4 t. And then now this one is going to be square root of 10 squared plus 50 squared over 10 integral dh. And what's the limits of the integral for the h? 0 to what? Zero to 10. Now comes the question, do we have to do any kind of unit conversions from miles to meters? We haven't done any of that yet. Is this it? Do we have to do conversion here? Miles to meters? No. Because this is miles, this is miles. It cancels. It's a ratio. So this one we don't need to. How about here? Well, this h is in miles. And then this is 0 to 10. I feel like we need some conversion here. Because this is meters per second. Or what if we did this?
Change the meters per second.
Change this to miles per hour.
Yeah.
Isn't that easier than worrying about this? Because this one, everything else is consistent. This is Celsius, this is Celsius. The idea of this two is cancels, Celsius, Celsius. So that this becomes unitless. 0 to 10, yeah, I think it's easier to change this to miles per hour. So meters per second, how do I convert to miles per hour? 3,600 seconds divided by 1609. Okay, now you've got to do this integral on the calculator. Function integral, okay? Might be too hard to do by your hand. 1 over square root of Okay, the integral gave me minus 1 plus 2. Okay, the integral gave me 9.82. 336. Then I multiply that by that. Okay, so T is equal to 67.55 milliseconds. Okay, so that's you're solving for this T. So you're doing this integral, 9.8, multiplying by that, dividing by this, and then multiplying by that ratio. Okay, so the sound wave, this is for the thunder. So the sound wave comes to you from the cloud, but as it's coming, the temperature is changing. You're accounting for all of that. This is the light, and then you subtract them. So it's not too much difference, you see. The light wave comes to you right away. So T thunder is going to be the delta T, I mean the difference of the two times is going to be this minus this. So minus 67.28. So 67.28 milliseconds. So now let's assume, to make it simpler, that the bulk modulus and density of seawater are constant, and it takes you 4.8 seconds to hear a sonar after sending it to the ocean floor. Sonar is basically like a sound wave. We use it to plot the map, the topography of the seawater under the ocean, right? So there's the ocean, and then the topography changes. You might go deep, you know. Then we take this sonar, we shoot it down, then it goes back, and as the ship is traveling, it can map out that topography. So assume the bulk modulus and the density of seawater stays constant, right? So here, what was the bulk modulus of seawater? We had that before, right? Did I write it? I think I wrote it. Did anyone remember? We wrote the bulk modulus of seawater.
2.34 gigapascal.
Yeah, 2.34 times 10 to the 9. And then we know the density of seawater back from the Archimedes' chapter, remember it was denser than regular water. So 1,030 kilogram per cubic meter. This is pascals. So we calculate the velocity of the sound in seawater. So that's going very fast, right? A lot faster than the velocity of sound in air. 1,507 times 10 to the 3 meters per second. So then what are you going to do? If it took you 4.8 seconds, that means one-way trip was 2.4, right? So the depth of the ocean is going to be the velocity of sound times time, half of the time that it took you to hear it back, right? So then that's going to be 1.507 times 10 to the third times 2.4. So this one is a more simple, we don't know integration, nothing. So 3.617 kilometers. Because 10 to the third is a kilometer. So, so you see, that's a good example of how you can map out the ocean floor. I don't know, is that deep for the ocean? What are like the deepest parts? It's about 1.5 miles. That's pretty deep. But I think it goes deeper, some parts of it. Yeah, so you can make a complete nice mapping. So it's a good example of the use of the bulk modulus and the density of seawater. Okay, good. So Wednesday then we'll do the intensity of sound waves. We'll get into some integration problems. We'll talk about the decibel scale, and then we'll end with the Doppler effect. Cool.